you for inviting us. It's a shame that we couldn't do this in person. I was so looking forward for that, but there we go. Okay. I'm going to take the lead to start off with, and then you'll see us flip backwards and forwards over this sort of fun thing. Okay. So let's start. So Grace, you're on the left. Do you want to introduce yourself?
Yeah. So hi everyone. Thanks for having us. So my name is Grace Jansen, and I'm a developer advocate at IBM. Interestingly enough, I'm actually a biologist turned developer advocate, and you'll see more of that as we go through the presentation. And yeah, I'm speaking today with Steve.
Cool. So Steve Poole. I used to work at IBM with Grace. I used to Red Hat as well. But currently I'm working at Sonotype. And my passion is and always been Java, but you may have seen a few talks I've done over the last few years around Java security and all those related aspects and developer productivity, and that's what I care about, and that's sort of why this talk exists. So we're not going to go into enormous details because A, we don't have time, and B, the subject is so big, but we're just going to wander around the comparisons between biology and Java and see how it stacks up and see what conclusions we can draw from it. So, there we go. I think I've just said this. We want to just get your brain thinking differently. And we're going to compare biology and the aspects of Java security. There isn't really much Java in it. There is a little bit, but mostly it's about just comparing how real world does it versus what we do in the computing space. Okay. So we will be learning a lot. We are obviously, as Java developers, we are quite disadvantaged because evolution has had a head start, quite a big head start. But hopefully we can actually, draw something fun from it. So we've broken this down into sort of 4 sections. Threats and challenges, which I'll do first because you need to understand the scale of things to make it real. Well, then we'll do prevention, which is, well, how do you stop getting it in the first place? What do you do to keep the bad guys out of your systems? Then we'll do detection, which is so they got in. Did you know? How do you know what they've done? What signs do you get? And then mitigation is not something really you can do after the fact, but it is something that you should be thinking about as to, well, if they do get in, how do you minimize the damage they can cause? And so we'll do those things, and we'll go wherever we go with this. So let me set the scene. The thing that everybody has to understand is that the whole space of bad actors has just grown dramatically. Whereas a few years ago we talked about people, hacking your systems for fun. Now there's no fun in it, and it's all for various nefarious needs, reasons. There's a lot of bad guys out there, and it's just getting worse. All the old things that you may have heard about, still happen. Drive-by attacks, which are where they just try and get into your system because you left the door open. They just found it. They get in. Open ports and things like that. There's still ransomware attacks. That's not going away. That makes an enormous amount of money for the bad guys. That's still going on. But the big thing, the big change in perhaps the last 18 months has been the realization of the fact that what everybody is trying to get to is into your supply chain. We're all part of supply chains. Whatever we do, they're a part of a supply chain. And supply chain, disrupting supply chains, whatever they be, is now turning into being a critical aspect of cyber warfare. And, given recent events, we know that this is true, and we're seeing it grow and grow and go. So think about this. So whereas before many people were just trying to steal your data for money aims, now they're trying to get into your systems, whether there's power supplies or into factories or even into the supermarket chains, because they want to be able to manipulate it at the right time. You can imagine what happens if you're trying to get a train and the train system has been disrupted. You can imagine what happens if you can't ship stuff because the shipping company has been disrupted. You can imagine all the problems. So that's the scale. It's turning into that sort of situation. Well, that's where we're going to go from. All right. So we have those. We have all the traditional reasons why people are trying to attack your systems. It's all becoming quite a large and complicated environment, but at the base of it is some basics of the basics. So they want to steal your data, obviously. They want to change your data, perhaps not so obviously. I want to get in and insert, perhaps I want to insert some credit identities in a credit company. Maybe I just want to change the address of where you ship things so that they go to me rather than to you. So changing data, crashing your systems, denial of service attacks, those sorts of things. Steal your compute power to do Bitcoin mining, which is the traditional reason for doing it, but actually for botnets and things like that, put in quiet ways. And obviously try and use your systems and yourself to go through your systems to get to somebody else to do the same thing there. They have these basic motivations. So bad guys on the outside trying to compromise your systems for their benefit. What is it like from the biological point of view? Grace.
So yeah, you might be wondering how this all fits together, right? Steve's gone through, okay, we're still under attack all the time from all these bad actors who have this variety of reasons for trying to get into your system. It's the same in biology. As human beings, our bodies are always under attack, and that's never been more clear than during this COVID pandemic. So there's a variety of different biological bad actors that are trying to get in. It ranges from viruses, like the COVID-19 virus, and then you've got bacteria, fungus, parasitic worms, protozoa. So there's a whole collection of things constantly trying to attack your body. And there's a variety of reasons that they do that. Why do they want to get into your body? Well, some of them use it as a host. Your body is a very warm, comfortable, and it's got plenty of food in it. So it's actually a really lovely place to live. So just using it as a host. Also to replicate and grow. We've got a fantastic system inside us that enables us to turn food and energy into replicating cells or creating functions. And if they're able to get in and use that cell machinery to make more of themselves, great. They get to multiply and spread further. So that's one thing they want to do. And to infect others, like Steve was saying, going through you to infect someone else. Same thing in biology, where you're seeing that it's infecting you, like the common cold, for example. How many times do we see adverts on TV or stories about, oh, remember to cover your mouth when you sneeze, use a tissue, wash your hands? Because as soon as we sneeze, we're spreading that all over the place for someone else to then be infected. And sort of more sinister is parasites. So things like parasitic worms, etc., literally using your entire body for its own benefit. So if you are squeamish, look away now, because it's a bit of a weird video coming up. But here's an example of what happens when a parasite gets in. So you'll see here, this is a beetle. And if you look closely, you'll actually see the inside of the beetle is completely hollow. So it is literally completely hollow on the inside. And you might be wondering, how on earth is it moving? Well, a parasitic worm has gotten into its brain and is literally controlling, like a puppet, controlling all the movements in that beetle to get it to a place that will benefit it and probably end up killing the beetle. So this is a really extreme form of a biological bad actor getting in, completely taking over your system and using it for its own benefit. So you can start to see some of the parallels coming in here. So let's take a closer look at those parallels. So Steve showed you before all of these reasons why bad actors are trying to get in. And as I said, really similar in biology. So where Steve said they're going to steal your data, yeah, parasites, bacteria, etc., they're stealing our resources, whether that's the cell machinery to replicate or our own energy. Changing your DNA. Actually, interestingly, some viruses can insert their own DNA into our DNA, and then when our cells replicate, it creates more of that virus. So they can edit our DNA, which is essentially the body's data. So crashing systems, I just showed you that beetle. That was a complete crash of the system. That parasite completely took over. Using your compute power, again, stealing our energy reserves. Power in the body is our energy. So bacteria and viruses, etc., are able to steal that, just like in Bitcoin mining. And then, as I said before, going through us to access others, spreading as far as they can and reaching as many people to get as many hosts as possible. So you can start to see where these parallels can be drawn between the natural world and software.
Cool. Well, let's compare them, shall we? Right, prevention. I think we start with you, don't we, Grace?
Yeah.
Yes.
Yeah.
What does the biology do? What does the body do to prevent it being attacked?
So we've got some amazing prevention strategies. It's called the innate immune system. So that just means it's innately there for us. So the first thing is we limit the amount of access points to the inside of our body. Our skin is a fantastic barrier to these potential infections, and we have a minimal amount of orifices. There's not that many entrances that infections can get in, our mouth, our nose, etc. But we've tried to keep it to a minimum. And at each of these openings, we have defenses in place. Things like saliva, for example, our stomach acid, tears in our eyes, mucus in our nose. So we try and have these defenses at the places we know are most likely for an infection to get in so that we can prevent that from happening in the first place. We also have developed sensors. So we have a really great sense, I mean, not compared to dogs, but our sense of smell, for example, is pretty good. If you go into a milk carton or a milk can and you smell that it's off, you're not going to drink it because you know it's not going to be good for your body. So having these developed sensors to be able to see, oh, that food looks a bit moldy, or oh, that milk doesn't smell right. Having these enhanced sensors, again, is prevention of getting that infection in the first place. As well as that, what you might not know is that on our cells, we have this cell membrane, and we have these proteins all around this cell membrane. And actually, these proteins help to identify these cells as ours. So as soon as we see a cell that isn't ours, we know it probably shouldn't be there. So our body works hard at trying to get rid of that and prevent that from happening. So having these ID tags really helps at sort of authenticating and authorizing, okay, yep, that cell should be there. We also have things like, pardon?
Like sort of zero trust.
Yeah, exactly, right? Just trust no one and check everything.
Yeah.
We also have things like scabs for wounds. If we get cut, that's a massive potential point of infection. That's an orifice that we did not want to happen. So we need to close that up as soon as possible. So our body's amazing at being able to quickly and really rapidly respond to that and close that up as soon as possible. Things like homeostasis, we're constantly monitoring, and even behavioral changes. So think back to the cavemen who discovered fire. Being able to cook our food, that helps prevent infection massively. Even more modern things like washing our hands and this year wearing masks. All of these behavior changes help to prevent that infection in the first place. So there's a whole plethora in biology just for prevention.
Cool. Wow.
Let's see how you compare.
Yeah, how do we compare? Well, there is stuff, obviously. The obvious ones are nowadays, if we're deploying to the cloud, there's always some API gateway. So it's not like a Java developer has to care too much about being the very front door. So the skin on this comparison, this is probably not something a Java developer cares about. So as long as they've got API gateways, at least that reduces the number of entry points. We usually have security systems. We have authentication processes. We do use those. And generally, there is some sort of input validation. So there is something that says, well, okay, is this data that's coming in correct? But I think, as we'll see, that's not necessarily good enough. But the thought is there. We have cool tools for managing our dependencies because, let's be honest, only 90% of the software that makes up an application comes from open source nowadays. So that means basically 90% of your application is written by somebody else. So dependency management, we know, is a really important aspect of keeping safe. And so we have those tools, trying to keep those bad dependencies out of the way.
Yeah, and I guess that's you wouldn't dependencies are essentially what we're relying on for application. You wouldn't want to be eating a piece of food that was off or out of date or etc. So you shouldn't do the same with dependencies.
Exactly. Yes. Yeah. I mean, our senses for that aren't particularly good. It's just basically somebody tells you that there's something wrong with this and you fix it. And then the CI/CD systems, if they're fast enough and automated enough, will keep the window of opportunity for that bad dependency down to a minimum. So we have what I think are the basics. Right. So I'm going to claim it's a draw. I may squidge it, but I would say there are some things that we should take away from this. Developers may not be the first line of defense, but they're definitely the second line. And there, as we said about washing hands and things, it's security hygiene nowadays has to be built into your processes. If you're not doing the right sorts of reviews at the right time, and you're not thinking about this, you're not thinking about prevention, and you're just relying on somebody else to do it, then that's not going to get you anywhere. If you look at from the, I've put the arrow to these bits from your list, Grace, and you can see, I would say there are some certain things that we go, that's us. As a developer, we may not be worried about the minimal orifices, that's the API gateway, and homeostasis, stuff like that. That's perhaps not us. But most of the others, they're definitely the first point of call is the developer. So I'm going to say it's a drawish.
Fair. I'll give it to you this time.
Okay. Detection. Okay.
Round 2.
Yeah, what happens when? So you have been unfortunately you have been compromised. Something has happened to your system. How do you know that you're ill?
So, I mean, in biology, we've had, as Steve says, we've got a big advantage here. We've had millennia to evolve and tune this very finely. We've got this is where the adaptive immune system comes in. So I said about the innate immune system, which is it just is there all the time. It's there to protect us. The adaptive immune system is all about adapting to potential infections that are already in, that we then need to detect to be able to tackle. So that includes things like your white blood cells, antibodies. So they're like these little Y-shaped things that you can see in the diagram here on the right. And they help to identify foreign bodies from those proteins on the cell membrane. Remember I was talking about the cell ID? We can immediately tell that's not meant to be here. So we need to get rid of it. So having this adaptive nature to be able to rapidly learn what's an infection, what's not meant to be there, what's harmful. Because you've also got to remember, we do still have bacteria inside us and on our skin that's good bacteria. So some of it has to stay. So we need to learn what's the good from the bad and get rid of the bad. So we're rapidly able to learn adaptively as we go. And that's why when we get a new infection, like when people were first ill with COVID, for example, it was a serious consequence because our bodies weren't used to it. But with the second infection, third infection, our body is able to identify these cells much quicker to be able to then detect them faster. And we use things like extra protection, like vaccines for this as well. That's the whole point of rolling out this COVID-19 vaccine, is that it gives us a dead or a fake kind of version of this, so our bodies can learn to identify it. So when we get infected with the real thing, we're able to detect it far quicker. And yet, even our own cells are trying to detect infections. So the individual cells themselves can detect when they've been infected, and they can signal to the rest of the body to say, kill me, I've been infected. So even they can self-sacrifice for the good of the body to be able to detect infection. And as well as our adaptive immune system, we also have pain. And you might not think of pain as a detection strategy, but actually, if I have maybe a stomach bug and my tummy's in pain, that's a detection signal to me through my brain to say, okay, you probably shouldn't eat anything else because we need to tackle this first before we can deal with anything later. Yeah. So that's another form of detection. And sometimes we can mask that with things like painkillers. So sometimes painkillers aren't necessarily a good thing because that pain is there for a reason. It's there to detect something that's wrong or got maybe an infection within the body. So yeah, loads of different ways to detect.
Yeah. I mean, the pain obviously is something that we don't really have. I like the idea of being able to have a cell signaling that they've been infected and being killed, and I think that'd be great on clouds. Yeah. Killed by Kubernetes. I know, that'd be cool. Yeah. So software. Well, unfortunately, pretty much the only way that we know that something bad has happened is through one of these horrible things that happen. So the obvious ones are your system crashes, and it might be repeating. Denial of service is those sorts of things where the system just dies or it's been corrupted. So that would be an indicator to you that you've been compromised. Your users might complain that performance is going down, And again, that may be that somebody's in your system and using your CPU, etc. There's software detection. Ransomware is much more in your face. That's when you try to log into your system and you find that you can't, or if you do, or your data has suddenly changed and got weird prefixes, and there's a note somewhere saying pay us loads of money or your data gets it. But that's pretty obvious. And then the other one is that at some point somebody tells you that the data that's in your system has been made available on the dark web. And that might be the bad guys literally tell you that, or it's recovered by one of the companies that out there that keep track of this and can spot that your data's been leaked. But that's pretty much it. It's pretty much gross. It's bad things have happened. Now you know. Right. Now, we have tools that, if they are being used, will help. And I think what this starts to show is that as a Java developer, it's certainly not your problem to fix everything, but it's definitely becoming more important, most important as a developer, that that the software that you produce works more effectively with the other tools that are out there to help. So, a microservice is not going to have a vision of a wide attack, because by its very nature, it's a very small thing. But there is monitoring software out there that watches what's going on, and they can analyze the logs and the requests coming in, and they can spot them. And there are some really good AI tools turning up that are learning more about how the attacks are formed. Of course, the attacks themselves are becoming more sophisticated, so that's a race on its own. But it is very much like you can show that your CPU usage is going up. You can show that you're getting authentication requests with the same user ID from 10,000 different IP addresses. You may not see it as a Java point of view, but there are other systems out there that can do that, right? But it's still indirect, because we don't really have any concept of saying, hey, my microservices tummy hurts. It's just not a thing that we have yet. Right. So let's just say biology wins. Yay!
But as we say, it's had a big advantage and a long time to learn. And really, it's vital in biology, because if we don't detect anything, then that infection could get to a stage where we can't do anything about it. So it is vital for keeping organisms alive and healthy.
Yeah, exactly. I mean, you've got autonomic systems, which we don't have in software in any general sense. But what I would say to developers when you start thinking about this is, go look at the monitoring solutions that are being used in your company. Go look at what the cloud services are offering, and learn a bit more about what information they want from you. And we'll talk about that in the mitigation sense. But it is not only about recording the obvious bad things that happen, but it's starting to put out signs that maybe that wasn't quite right. So if I've got a field and I expect it to be in the range of 1 to 10, and you expect most of the time it will be in the middle, if you start getting numbers that are in the out of range that you weren't expecting, they may still be valid, but they may be suspicious. So start recording the suspicious behavior, so the monitoring solutions can start to see that. If you give out those sorts of clues, then there's a chance that something else will pick up on it. If you don't do that, then nobody knows that bad things are happening. Okay, round 3, mitigation.
Bring it on.
This is a longer one.
Yes. So how do we, once we detect something, how do we actually deal with it? What does the body do to deal with it? Well, as I mentioned, we have behavioral changes. So introducing things like vaccines is a form of mitigation in terms of training our body ready for when it does get infected with the real thing. I also mentioned the adaptive immune system. Being able to rapidly learn so we can then ID it and destroy them is also important. Another thing you might not think about is your body is amazing at making itself a rubbish place to live when it realizes it's infected. So you might hate it when you get, say, a flu or anything like that, and you start to get a fever, for example. Your body gets really hot, you shiver, etc. And that's your body's way of making it a really uncomfortable place, deliberately. And although it's annoying for you, it's one of the best ways we have for making it much harder for infections to thrive within our bodies. So making it harder for them to spread and grow so that we can then tackle the limited number that we've been infected with.
Yeah.
Getting rid of them. That's a big one. That's like the whole point of mitigation. So our body has multiple ways to get rid of them. Our white blood cells often essentially eat them and destroy them with various different proteins and things, as you can see in the diagram here. But also things like vomiting, so throwing up, and also the other way as well. I'm sure we've all experienced it at some point. Maybe if you had food poisoning ever, our body is essentially trying to expel anything that's infected, especially if it's within your stomach or within your food. Another thing is our bodies are amazing at creating solutions to this. So for example, I mentioned that some viruses try and insert data into us, so changing our data, changing our DNA. And our body has come up with a solution to coat our DNA molecules so that viruses can't insert their information into our DNA. And then other things like just having patrols. So our white blood cells are constantly monitoring, going through our blood circulation, just checking everything's okay and being there, ready to pounce on anything that shouldn't be there. So all of this is mitigation, trying to prevent that infection. And once it does get in, dealing with it and trying to kill it before it kills us.
Yeah. So I honestly, there's some really good ideas here that maybe we can apply to software. I think, to be honest, most of these are way in advance of what we can do now. But people should think about it. Maybe we can come up with some software solutions. A couple of Quarkus plugins, please. They help us. So, what can we do from a software point of view? Well, there's a few. I'm not going to spend much time. I'm just going to lay them out for you. Most of this, we talk mitigation. Again, this isn't what you do after the fact, to be honest. It is stuff that you should be designing in so that when it does happen, the damage is limited. The first one, obviously, is there have been lots of good advice on how to design secure systems, right? And here's one, OWASP, I'm sure everybody knows who that is. They have security by design principles. There's a whole bunch of stuff there. That's a day or a week on its own. But obviously, if you're not paying attention to even the basics, that's not good. There are some interesting things related to code quality. If you have poor quality code, if you have lots of technical debt, that actually makes you more vulnerable because that means your systems tend to be more or less robust, less harder to understand, and complicated code tends to have edges that the bad guys can exploit. So actually, good quality code makes you safer. There are things that we do that we could change in the way that we structure data. We're very good at creating systems that are designed sort of for the developer's benefit rather than for the end user. It's just easier if we do it that way. Classics like sharing all the data when you only need to share part of it. So for instance, here you might have a situation where you've got a name, you've got somebody's account and address. You don't want to give out their email addresses if your email details and postcodes and phone numbers if all you want is their address. So you write your use cases, you organize your APIs around the data structures that you need to deliver, and you deliver only that. You just don't give them everything else because you're limiting their ability to access your data. They've got to compromise the other API to get at that data. And little things you can do is don't give out raw data. Think about how easy it is for somebody to make use of the data you give them. So if you give out dates, for instance, in this example, but it could be anything, then make them work for it. Don't give them out raw dates. Give them something like in the second example where there's some starting conditioning, you give offsets. Just make it harder for the data to be consumed. Because there are a bunch of guys out there who are just going to scrape it. And if it doesn't work on the first go, it's not useful, they'll go somewhere else. And the other big classic, the thing that developers do from a design point of view, is we tend to do this sort of all or nothing user authentication and security powers. I have nothing or I have everything. And don't think of it like rings of onions. Really is think about it as support, give people powers based on the role they're doing, construct your system around those further bases, as you can see in these diagrams. Right. Report unexpected behavior. I've touched on this. This, I think, is one of the things that we just don't do, and we need to get really better at this, which is when you have an interaction with the client, your own microservice may be considered to be stateless, but the data structures, the state of your client's data is not. And a lot of this is about thinking about whether the request that comes in is reasonable. A lot of this is about recording and the fact that a suspicious behavior has taken place. So that's really important to start thinking about how you design software to spot that it's not bad, but it's suspicious. And things like dealing with errors is really cool. How many people have done the little red box where you say, oh, I got an exception. Yeah, I was expecting it, so it's okay. And we all frown on it, but we all do it. Being able to think better about the error path that you have in your application, be much more specific about the errors that you catch and what are possible, and report the ones that you expect, but also report the ones that you don't expect, but report them in different ways so that they can be spotted by these monitoring tools. If you just swallow it, then nobody knows. And this one people may not even think about, but test your dependencies. Recently, we had this little tiny thing in the press, you may have seen, where somebody took their node package, in this case, node IPC, and they changed it so that suddenly it would wipe the machines. You can read all about it. The point is that you cannot depend on your dependencies to behave the way that you expect. So if you haven't got tests in your system to prove to yourself that it's doing what you expect, how will you catch it when it does something wrong or different? Okay. 90% of our software it comes from open source projects. Open source projects that have poor security hygiene, of which frankly there are many, are themselves targets for hackers, and they get compromised. So believe me, when you're selecting software, don't select it just for the features. Go have a look at the project and work out whether you think they have their own security good practices, because the ones that don't are more likely to be compromised than the ones that do. There we go. Mitigation summary. Biology.
I mean, there's a reason that we're so good at mitigation, and that's because, as Steve said here, there's no reboots in biology. It's a lot of the time the risk, if we don't do something about infections or viruses or parasitic ones, etc., is often serious illness, if not death. And so it's really critical for us, especially because our environment is constantly changing. Viruses are constantly adapting to try and get in. So these attacks are inevitable. It's going to get past our defense systems at some point. So we have to have the mitigation strategies in place to be able to deal with those ever-changing infections and bad actors. So yeah, there are some serious consequences in biology.
Yeah, I mean, having said that, you've got evolution obviously learned, because the things that work that fail obviously get edited out of the gene pool. Software doesn't have that opportunity because we're talking about real lives, real data. There are no reboots, but we have to think so much more now, because the consequences for being attacked, for losing data, for what the bad guys are trying to achieve are just becoming more and more serious. So we really have to look much harder at the way that we create and design software. Right. So this Mother Nature.
I mean, it wasn't really a fair competition. But I think from this analysis, we can start to take away those comparisons and start to take away, okay, maybe I should be taking some of these biological behaviors or evolutions and applying them into my software system.
Yes. So what do we have next? Oh, roundup. Yes. So we have, I think, one slide about some takeaways, but what I've learned talking to you, Grace, and just walking through this is obviously you can compare. You can use biology as a really good set of examples. Now, obviously, biology having millions, billions of years of progress and this ability to naturally select, which we don't have. But having said all that, I still look at it and go, there's a whole bunch of good ideas that are in there. We don't have any way of creating those self-learning programs, and I'm not sure that we want to in the first place, but we're not there. But I do think, having looked at all this stuff, that there's some really cool ideas, and I'd encourage the people out there who are watching us to be inspired by nature and maybe think of new ways of writing software and not just doing it the old way. Let's have some new styles of application.
Yeah, I think we're tight on time, so takeaways?
Yeah, takeaways. So what do we say? So I think we just said this. At the end of the day, from a software point of view, you have to design for defense in depth, and you'll hear about that if you read about it. It's from the API gateway down, but there's lots of things. There's about validating input for sure, which means doing it more stringent than we do today. The OWASP space will tell you not only how to do it, but also what the bad guys do, because it's quite a fascinating space itself, but it's important. Highlight unexpected behavior. Yes, so we're so used to saying we'll report an error, but we don't report these suspicious things because we're not really sure what they are, but we need to get better at doing that. Keeping defenders up to date is like the most obvious number one activity, regardless of anything else, because that's the biggest source of attack. Take a zero trust approach. Work on the basis that nothing you use is trustworthy, and work up from there. And lastly, the most importantly is take a look at the software that you're connected to. Go look at the API gateways and look at the monitoring tools and see how you can work better with them. Because one thing to remember is the only thing between you and the bad guys is software. So you want to make sure that that chain of software is the best it is and works the best. You're only one cell in the system, but you should be the best cell.